Hello students, good morning. I hope all are doing good. Hi everyone, good morning. Harshini, good morning. Avanti, good morning. Ratan Kumar, good morning. Joshnavi, I guess, good morning. Kiranya, good morning. Sonia, Siona, I think Sonia, okay, I'm sure. Siona, good morning. Isha, good morning. Shall we start the class? Just try to recollect the points which I have given in last class. In last class, I started a topic named as hybridization. As I told, hybridization concept is most important concept under chemical bonding, which we will be studying in first year course. Hybridization, I have given the definition and important points about hybridization I have given, conditions for hybridization I have given, and I explained the types of hybridization also. I hope all of you guys have followed the class. I hope you are able to recollect the shapes which I have given in last class. Okay. So once again, a very warm welcome for today's session. We will be starting this session, and as I told you, please focus on the class and listen properly, and if possible, try to note down the points. Okay, this is most important topic under first year course. Okay, right. Okay. Try to check out this table. This is the summary of the points which I explained in last class. Yeah, yes, you can raise your doubts. Okay, Charanya, yes. Very good. If you are noting down all the points, it is awesome, very nice. And if you can note down, it would be really helpful for you. After taking the class, if I am trying to note down or if you are trying to note down, it would be benefited to you only. Okay. I am good. Okay, let's start the class. Yes, myself, Ram Babu. Okay, so here I will be called as RBM. Okay, so yeah, okay, let's carry on let's try to start the class. Okay, very good. All are toppers. Okay, so all are toppers in our class. Super, very good. If it is the case, it is very nice. Okay, right. In last class, we discussed about the geometry. Of course, you can sometimes refer it as shape. Here, this is the number of orbitals which are involved. Of course, the same number is also the number of hybrid orbitals. Okay. If two atomic orbitals have involved in a particular hybridization, gives two sp hybridized orbitals. Two sp hybridized orbitals are aligned in linear shape. I have given here shape or geometry. With linear shape, bond angle is 180 degrees. No need to recollect these examples. We will be working on the examples. Okay, if I am going for the combination of three atomic orbitals produces three sp2 hybridized orbitals, and these three hybrid orbitals are aligned in trigonal planar geometry. And here the bond angle was also mentioned. Bond angle was 120 degrees. Good. If four atomic orbitals have involved in hybridization produces four hybrid orbitals, those four hybrid orbitals are sp3 hybrid orbitals. All the four sp3 hybrid orbitals are aligned in tetrahedral geometry. Okay. If five atomic orbitals have involved in a particular process or hybridization produces five hybrid orbitals. These hybrid orbitals are represented as sp3d hybrid orbitals, and these are aligned in trigonal bipyramid geometry. If you are talking about trigonal pyramidal bipyramid geometry, the bond angles, possible bond angles are 90 degrees and 120 degrees. I will show the bond angles after writing the geometry. And the six atomic orbitals are resulting into the formation of six hybrid orbitals. Those six hybrid orbitals are represented as sp3d2 hybrid orbitals, and these are aligned in octahedral geometry. I hope you are able to recollect all these geometries. Students, you guys tell me, if seven atomic orbitals have involved in hybridization, produces how many hybrid orbitals? Seven atomic orbitals are involved in hybridization, produces how many hybrid orbitals? Seven hybrid orbitals. These hybrid orbitals are represented as sp3d3 hybrid orbitals. Okay. These seven hybrid orbitals, I have given the geometry in last class. These seven hybrid orbitals are aligned in pentagonal bipyramid geometry. You have to remember all these geometries. Okay, very good, very good. Right? Okay, now quickly have the recollection of all the geometries. Okay, in sp hybridization, we will get linear geometry, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramid, sp3d2 octahedral, and sp3d3 pentagonal bipyramid. Okay, I hope the points are clear. Now the next task for us is to predict the hybridization of a given compound. I mean, whenever we are referring hybridization, hybridization is predicted for the central atom of a given species. Okay. Now moving ahead. Okay. Explanation. Consider with an example formation of, theoretically I will explain example. Students, please focus on the class. Don't be distracted or diverted with any unnecessary chatting. Okay? Focus properly in the class and follow the lecture properly and try to learn the concept in a proper manner and in a easier manner. Okay? Fine. Formation of BeCl2 I am not going to explain the formation of molecules. Listen properly, students, listen properly. Here we are not going to discuss many examples, theoretical explanation of hybridization. I am not going to explain for many molecules. Okay. As I told, I have very easy short trick method by using which we can predict the hybridization of a given species. Okay. Right. Ultimately, in objective examination like NEET examination, you need the quick solving probability or possibility of questions. Okay. Fine. So formation of BeCl2. As I mentioned in last class, hybridization is predicted for the central atom. As I told, under synopsis of hybridization, atomic orbitals of central atom involves in hybridization. Here central atom is beryllium. And electronic configuration, as I refer electronic configuration, always we will deal with valence electronic configuration of beryllium. Okay, it is 2s2. Of course, there is 2p subshell but with 0 electrons. Why I am trying to introduce this 2p subshell? Listen properly. Beryllium has to form bonds with 2 chlorine atoms. Okay. For that, beryllium has to have 2 singly occupied orbitals. But if you write the electronic configuration of beryllium, here there is no single electron. Okay. Now what I am trying to do, if I can send the electron from 2s into 2p, I can be able to explain the formation of BeCl2. You will be having doubts, sir, how to know when to send the electrons from one orbital into another orbital when it happens. Okay, during the hybridization, depending upon my requirement, promotion of electrons takes place from one orbital into another orbital. It is not necessary for all the cases. It is not necessary for all the cases. It is all depending upon the situation of the molecule, depending upon the requirement. It is not necessary condition. It is not necessary the promotion of electron always takes place in a given hybridization. It is not necessary condition for all the cases. Okay, it may be depending upon the requirement of the given compound. Right? Now I need to send this electron into excited state. Here I used to refer it as excited state. You may be having doubts, sir, what is excited state? It is very simple. Excited state means sending electron from lower energy to higher energy. Okay, excited state means excited, high energy state. It is simply high energy state. So sometimes used to refer, are you excited? Okay, if you are excited, you are with high energy levels. Here the electron from 2s need to be sending into 2p. So for this we are referring as excitation. Okay, so one of the electron from 2s is sending into 2p. Now we are ready with hybridization. Now look at carefully. Now we have one s orbital and one p orbital. These two orbitals are intermixing together and forms how many sp orbitals, sp hybrid orbitals to sp hybrid orbitals. So when the process of hybridization is sp, or in a given hybridization, here two hybrid orbitals have formed, then how these hybrid orbitals are aligned? How these hybrid orbitals are aligned? Can anyone tell me? These hybrid orbitals are aligned in which geometry? In which geometry? As we know, hybrid orbitals are represented with this symbol. these two hybrid orbitals are aligned in linear. Okay, this is one sp hybridized orbital of beryllium. This is second sp hybridized orbital of beryllium. Now, these hybrid orbitals are ready for bonding. Now, we have to make this chlorine atom ready for bonding with sp hybridized orbital of beryllium. Now, if you talk about chlorine electronic configuration, if you can write, valence shell configuration of chlorine has 3s2 3p5 configuration. 3s is anyway, it is completely filled, and 3p follow Hund's rule, and if you fill the electrons into 3p subshell, there is one singly occupied electron in 3p subshell. Now, even chlorine is also ready with half-filled orbital. Now, the hybrid orbital of beryllium is also ready. Now, these hybridized orbitals of beryllium are forming bond with 3p orbital of chlorine, which results into the formation of sigma bond. And in the same manner, the second hybridized orbital of beryllium forms sigma bond with 3p orbital of second chlorine. Okay. Now, here these two bonds, if I talk about the bonds which are formed between beryllium and chlorine are sigma bonds. As I mentioned in last class, hybridized orbitals are allowed to form sigma bonds. Okay, there are two sigma bonds which are formed between each beryllium with chlorine atom. Beryllium with chlorine atom. This sigma bond is referred as sigma spp, and this sigma bond is referred as sigma spp. Why? Because beryllium's sp hybridized orbital is forming sigma bond with p orbital of chlorine. Hence, the sigma bond is represented as sigma spp. As we have already discussed, the bond angle under sp hybridization would be 180 degrees. I hope this is clear. Right? Now, we have discussed formation of BeCl2, and I'll explain one more example for better clarity. Okay? Fine? So, shall we move on to the next page? With this example, things will be very fine. Okay? Now, try to explain the formation of methane molecule. I will explain the formation of methane molecule. Listen carefully and follow the points carefully. Here the central atom is carbon. Central atom is carbon. Point number 1. Then what are side atoms or surrounding atoms? Side atoms. What are side atoms? We have hydrogens are side atoms. How many side atoms we have or surrounding atoms we have? In total 4 surrounding atoms we have. Now tell me one point. Listen students carefully. Let me ask you a question. Now who is being involved in hybridization, or orbitals of which atom is being involved in hybridization? Atomic orbitals of central atom is going to be involved in hybridization, or the surrounding atoms atomic orbitals? Yeah, yes. B is actually, it is a limitation of octet rule. B is able to form only 2 bonds with chlorine atoms. Okay, it can form here in this example 2 bonds I have given. It is the example of limitation of octet rule. Okay, here B is not following octet rule. It can be called as incomplete octet. Okay, so central atom is carbon, and atomic orbitals of central atom only involves in hybridization. Atomic orbitals of side atoms are not going to be involved in hybridization. I think I have given the points in last class. This point is clear. So we are going to explain the hybridization with atomic orbitals of carbon or atomic orbitals of hydrogen. Students, tell me. Response please. Atomic orbitals of carbon are going to be involved in hybridization, or the atomic orbitals of hydrogens? Okay. Good. So atomic orbitals of central atom involves in hybridization. Now the electronic configuration of carbon, valence shell configuration of carbon is 2s2, 2p2. We have practiced electronic configuration. Now if I am writing the electronic configuration with orbital notation or with box notation. Now if you observe the representation of electrons, okay, here carbon needs to be accounted for how many bonds? 4 bonds. But I am having only 2 singly occupied electrons. For the formation of bonds with 4 hydrogen atoms, we need to have 4 singly occupied electrons. For this, I need to send the electron from 2s into 2p. This process is called as excitation. Okay. So for excitation, energy is required. So energy will be automatically sufficient during the formation of the bonding. Okay. Therefore, the promotion of electron from 2s into 2p takes place. Why the promotion of electron from 2s into 2p takes place? As I told, we have 4 hydrogen atoms. These 4 hydrogens need to be forming bonds with carbon. Each hydrogen is, if you write the electronic configuration of hydrogen, there is only 1 electron in the 1s orbital of hydrogen. Therefore, if this hydrogen is forming bond with carbon, carbon should be having singly occupied orbital. Therefore, to account for bonding with 4 hydrogens, carbon need to have 4 singly occupied electrons, since carbon need to form 4 bonds with 4 hydrogens. Therefore, now I should make this s orbital and 3 p orbitals in process of hybridization. Hence, the hybridization of carbon in methane is sp3. In sp3 hybridization, as we know, 4 hybrid orbitals have formed. All these 4 hybrid orbitals are aligned in tetrahedral geometry. Now carbon's 4 sp3 hybridized orbitals are represented in this way. Now hydrogen, if it is ready, we will try to make the bond. Now hydrogen is also ready. Now therefore hydrogen 1s orbital is approaching towards sp3 hybridized orbital of carbon, and which leads to form a sigma bond. In the same manner, all these 4 hybridized orbitals are forming 4 sigma bonds with 1s orbital of hydrogens. I hope this point is clear. Okay. Now carbon is forming 4 bonds with hydrogens. All these 4 bonds are sigma bonds. And the bond angle between any 2 bonds is 109 degrees 28 minutes can be written, or in short 109 degrees, 109.5 degrees. You can write any of these. And the 4 sigma bonds are formed between sp3 hybridized orbital of carbon and s orbital of hydrogen. I hope things are very clear with this example. Okay, this is the theoretical explanation of hybridization of a particular atom in a given compound. Now we are going to work on the short trick method. This method is very simple method. It works for all the examples which are given under chemical bonding, and it is very simple and handy. You can apply in a better manner. Okay, fine. Shall we close with this? I have given 2 examples for explaining hybridization. Okay, one example is BeCl2, the other example is formation of methane. We can explain many examples theoretically by using this procedure. Okay, but we are concerned about the shortcut way of prediction of hybridization. Who is going to write all these steps and details? Okay, in NEET examination, each question is almost allotted like 1 minute. Okay, within a minute, like chemistry, you will be allotted 60 minutes. Just before 60 minutes, you have to complete all the questions. So therefore, you need to do quick calculations and you need to have grasping skills. Okay, I will talk about all these details in upcoming classes. How to attempt the exam, what skills are required for attempting the exam. Okay, you need to solve the hybridization very quickly. Okay, right. Follow this properly. We are going to work many examples. Okay, listen properly and follow things properly. Here, total number of hybrid orbitals. Okay, this number can also be called as steric number. Okay, which is equal to total number of sigma bonds. Okay, plus total number of lone pairs. Sir, how to find out the total number of sigma bonds, and do we need to draw the structure? No need of drawing the structure. Total number of sigma bonds, it is the total number of surrounding atoms itself. Total number of surrounding atoms or side atoms or surrounding atoms. Okay, clear? If the steric number is, if you are getting HO as 2, okay, if number of hybrid orbitals are 2, what would be the hybridization? sp. And if the HO number you are getting it as 3, the hybridization is sp2. And 4 sp3 hybridization and 5 sp3d hybridization, 6 sp3d2 hybridization, and if you are getting the number as 7, it is sp3d3 hybridization. Okay, is this point clear? First, we are trying to count the steric number or hybridized orbitals count. Hybrid orbitals. Number of hybrid orbitals is equals to total number of sigma bonds plus total number of lone pairs. Okay. Total number of sigma bonds itself is total number of side atoms. Okay. So, if the hybridized orbital count or steric number is 2, then its hybridization is sp. If steric number is 3, hybridization is sp2. If steric number is 4, sp3 and so on. Right? Shall we go for calculation of hybridization? Shall we? Is this point clear? Is this point clear? Students, shall we move ahead? Okay. Now, here you may be having doubts, sir, how to find the total number of lone pairs? Total number of lone pairs calculation. What do you mean by lone pair? As I have mentioned already, this is the pair of non-bonded electrons. Okay? Non-bonded electrons. Non-bonded electrons remains as pairs. Such pairs are called as lone pairs. Such pairs are called as lone pairs. Right? Clear? Let's take an example. Let's take an example of methane. Let's try to apply methane since we have discussed just now. Who is central atom over here? Central atom is carbon. Carbon has how many valence electrons? I am writing the valence electrons. These are the valence electrons of carbon. Carbon has in total 4 valence electrons. Carbon has 4 valence electrons. I have written. Each valence electron is forming bonds with whom? Hydrogen. Okay. So, for hydrogen, 1 electron is required, second hydrogen, third hydrogen and fourth hydrogen. Do we left with any non-bonded electrons? Do we left with any electrons which are not bonded? Or all the electrons which are present or the valence electrons of carbon, the 4 electrons have involved in bonding. There is nothing left as non-bonding. Therefore, what is number of lone pairs count over here? What is the number of lone pairs count over here? There is no lone pair count. Therefore, in methane molecule, number of lone pairs is 0. Then what is the number of sigma bonds? As I told, the total number of sigma bonds is equal to total number of side atoms only. Therefore, the hybrid count or steric number count for carbon in methane is, can I write 4? What is this 4 stands for? 4 is the number of sigma bonds or surrounding atoms plus lone pairs 0. 4. If steric number is 4, what is hybridization? sp3. Is this point clear? Is this point clear? Let's try to work on another example. Okay, I'll move aside. Okay, I think this page, you can take the screenshot of this page. Shall we move on to the next example? Next example. Next example. Example number 2. Example number 2. Right? H2O. Who is central atom in H2O? Central atom is oxygen. Right? Oxygen has how many valence electrons in its valence shell? How many valence electrons are present in oxygen? In total, there are 6 valence electrons in oxygen. I have given the information about valence electrons in the periodic table. I think I have given, please recollect once. Oxygen belongs to 16th group. Oxygen belongs to 16th group, hence it is expected to be having 6 valence electrons. Can anyone find the hybridization of oxygen in H2O? Oxygen is bonded to whom? Hydrogen. For each hydrogen, oxygen need to use how many electrons? Single electron. Out of 6 electrons, I am able to use only 2 electrons. How many electrons are being left? How many electrons are left? 4 electrons are left. As I told, the non-bonded electrons remains as lone pairs. So total number of lone pairs present on oxygen. Tell me students, here totally 4 electrons we have. and all the 4 electrons remains as how many lone pairs? 2 lone pairs. Now try to calculate HO. Now the HO for oxygen is, we have 2 surrounding atoms and how many lone pairs? 2 lone pairs. We are getting the hybridized orbitals number as 4 and therefore the hybridization is sp3. Clear? Next, moving on to the another example. Example number 3. NH3. I need the hybridization of central atom only. Who is central atom in the given molecule? Nitrogen is the central atom. You may be having doubt, sir, how to guess the central atom or how to find the central atom. I have some hints to predict the central atom. I'll explain. Okay? Right. Try to predict the hybridization of nitrogen in ammonia. This is ammonia. As we know, ammonia. You need to remember some compounds. Names of some compounds you need to remember. Now, nitrogen belongs to 15th group and has how many valence electrons in its valence shell? Totally 5 valence electrons are present. Out of 5 valence electrons, how many are being used for bonding with hydrogen? As you know, hydrogen is monovalent. Hydrogen is able to form only single bonds. I have 3 hydrogens. So nitrogen is using its 3 electrons out of 5 and 2 electrons remains as 1 lone pair. Therefore, steric number for nitrogen in ammonia is, there are 3 surrounding atoms and 1 lone pair. Altogether we are getting 4 and 4 means hybridization is sp3. Is this point clear? Moving ahead. Okay. Can anyone tell me the hybridization of nitrogen in NH4 positive? NH4 positive. Right? Okay. Now again the same procedure. Central atom is nitrogen. Nitrogen has in total 5 valence electrons, but out of 5, how many is supposed to be lost? Okay, and we need to subtract the positively charged units. Valence electron count minus number of positive units, each positive charge. As we know, positive charge refers the loss of electrons. So from the valence electrons, we need to subtract the charge. How many charges we have? Only one positively charged unit we have. Therefore, 5 minus 1, 4. We have totally 4 valence electrons. Now tell me students, all these 4 valence electrons are forming bonds with hydrogen. Do we left with any lone pairs? Here lone pair count is 0 and sigma bonds count or surrounding count is 4. Therefore, hybridized orbitals of nitrogen is, total number of surrounding atoms are 4 and number of lone pairs are 0. We are getting 4. 4 means hybridization is sp3. Okay. I hope you are following. Example number 5. Example number 5. Okay. Example number 5. Try to calculate the hybridization of carbon in CO2. Can anyone tell me the hybridization of carbon in CO2? Try. Students, responses please. So from here after you will come across with very important and interesting questions. So prediction of hybridization is most important topic. You need to be thorough with prediction of hybridization. You need to learn in a proper manner. Okay? Right. So what is the hybridization of carbon in CO2? We have conventional formulas also. After familiar with this short trick method, If you want me to give, I'll give formulas. Okay, but believe me, this kind of process will help you a lot. This is most easier way you can predict the hybridization. But some formulas required calculations. If you are going for calculations, you may commit some mistakes in simplifying them. Here there is no need of any calculation. If you practice properly this process without using pen, paper, you can predict the hybridization of given atom in any species. You can find out. Hybridization prediction would be most easiest part if you follow this process. Okay. Now, who is central atom here? As we know, carbon is the central atom, and carbon has in total how many valence electrons? We have four. Very good. Many of you have given good answer, correct answer. Superb. Hybridization is sp hybridization. Very good, very good, very good. Okay. Now, this carbon has to form bond with oxygen. As we know that oxygen is divalent. Can you list the elements which are divalent? As we know, oxygen, sulfur, you can say. Okay. Monovalent, I think you can give many examples. First and foremost comes in the list is hydrogen, then fluorine may come, or like chlorine, bromine, iodine. Provided when I am considering these fluorine, chlorine, bromine, iodine, if you are considering them as surrounding atoms, monovalent, let me write surrounding atoms, divalent, surrounding atoms. I am not considering them as central atom. If chlorine or bromine or iodine are there as a central atom, the story will be different. Now we are considering them as surrounding atoms. Trivalent, most frequently used atoms, I am writing nitrogen, you can consider. Okay, surrounding atoms by keeping in mind of surrounding atom. Now since oxygen is a divalent atom, for each oxygen carbon has to use how many electrons? 2 electrons. Again, second oxygen I am having. For 2 oxygens, carbon has to use all of its 4 electrons. Do we left with any lone pairs? We are not left with any lone pairs. Therefore, hybridized orbital count for carbon in CO2 molecule is, here we have 2 surrounding atoms and it is not having any lone pairs. If you are getting number 2 as steric number, hybridization is sp. So I am going to give a chocolate question. Try to answer properly and give the correct responses. Okay. Can anyone tell me the hybridization of, it is simple question only. I think example 6. Okay. 6. Example 6. Okay. Very simple. It is chocolate cost will be very less, I think. It is simple question. Okay. What is the hybridization of sulfur? I need to get the hybridization of sulfur in SO3. Yeah, tomorrow, wait for tomorrow's class. Tomorrow is the, I think I can say, we will work on some more interesting questions, some more previous year questions. Okay. Now tell me the hybridization of sulfur in SO3. Hybridization of sulfur in SO3. Very good. sp2. Students, I think you might be having thinking sir, what are the ingredients or what are the requirement to calculate hybridization of a given element? Okay. After working on these examples, you must be knowing about the valence electrons of the central atom, number 1. And number 2, you need to know the valency of the surrounding atoms. Valency means combining ability only. Hydrogen is monovalent, oxygen and sulfur are divalent, and halogens, if I am considering them as surrounding atoms, those are also considered as monovalent. Very good answers. Sulfur belongs to 16th group, has totally 6 valence electrons. Sulfur has to form bonds with 3 oxygen atoms. As we know, for each oxygen 2 electrons are required. There are in total 6 valence electrons. All the 6 valence electrons of sulfur are consumed. There is nothing left as lone pairs. Here lone pair count is 0, and the surrounding atom count is 3. Surrounding atom count is also as known as sigma bonds. Okay. Now what is the hybridized orbital count of sulfur in SO3? Okay, 3 plus 0, we are getting 3. If 3 hybridized orbitals are present, its hybridization is sp2. Okay, students, try these examples also. Tomorrow we will discuss about these examples. Try the hybridization of phosphorus in PCl5 and the hybridization of sulfur in SF6. Okay, right? Try to predict the hybridization of phosphorus and sulfur in the given molecules. Okay, so don't miss the next class. Next class is going to be very important class. Okay, because we will try to work on all the examples which are given in your chemical bonding chapter in a best way and in a easier way, in a shortcut way. Without using pen, paper, you can work the questions easily, right? Okay, so with this I will stop for today's session. Okay, please try to go through the points which I have given and use the short trick method for prediction of hybridization, for predicting the hybridization for examples which are given in your textbook. Okay, right, I hope you have given the answers for PCl5 and SF6. Okay, and the hybridization of phosphorus in PCl5 is sp3d, and the hybridization of sulfur in SF6 is sp3d2. I hope all of you are getting the answers. Okay, so that's all for today's class. Thank you and have a nice day.